All right. So hello, everybody. It's the day before the exam. How are you feeling? Are we okay? Good? Bad? Please tell me how you're feeling in the chat while I kind of tell you what we're doing today. Oh, you know what? The number scale works really well. Let's say 0 is I didn't even know there was an exam, and 5 is I'm ready to crush it. Give me your rating while I explain what we're going to do today. So, I made a set of practice problems, as I told you guys before the exam review. We didn't get a chance to do it during the exam review, so I just compiled a bunch of the questions into like a packet, and I put it on Canvas. I also sent an email, but I don't think the email was sending. I think it was saying the file was too large. I'm not sure if that was this packet or the notes packet. Either way, both of those are on Canvas. So today, we're just going to go through and do all of these questions. If time permits at the end, maybe we'll review any concepts that you all have questions on. All right, so everyone is between 3 and 4, which is amazing. I'm so happy to hear that. Okay, if anyone is feeling like lower than that, but they just don't want to say it, that's okay too. If anyone is feeling like super confident, that's awesome. But hopefully by the end of this, you'll feel at least like 0.1 better. So let's go ahead and get started. Also, disclaimer, I am going to be asking for a lot of participation, but also I'm going to show you the Rosemary method of answering these problems. So it might go kind of quick. If you have any questions, don't be afraid to stop me. Okay. So first and foremost, we know this is about aromaticity, so I want you to go through. This one says anti-aromatic. Very important. Which one would you expect to be anti? And we know that the anti is 4n pi electrons. So I'm going to go through these. This is cyclic planar fully conjugated, and it has 2, 4, 6 pi electrons. So this one is aromatic. This one is cyclic planar fully conjugated, but it has 1, 2 pi electrons. That's actually still aromatic. This guy, cyclic planar fully conjugated, 1, 2, 3, 4 pi electrons. 4 pi electrons means anti-aromatic. This one is benzene. We know benzene is aromatic. You don't even have to look at it. This one, cyclic planar fully conjugated, 2, 4, 6 pi electrons, so we know that this is aromatic. So the answer here would be C. And yes, I can explain the first one. So here it is cyclic. We know that it's less than 8-membered ring, so it's going to be planar. It's fully conjugated because it's double bond, double bond, double bond, double bond, anion. And if we count electrons, we know that there's 2 electrons per double bond, so 2, 4. And then we're going to count the lone pair, so 5, 6. So that would be 6 pi electrons total.
This one here.
Does that make more sense?
Yeah.
You do count the anion. So you have to count the lone pair from the anion. So that's why we have 1, 2, 3, 4, 5, 6. So it's 6 pi electrons. Yeah, exactly. So the lone pair is from the anion. Exactly. Sometimes he'll only do the minus, sometimes he'll do both. Try not to get too tripped up on it because it can be a little bit weird. Okay. So for the next one, also please don't mind the number order for this one. Like all of these are out of order, but that's okay. So again, first thing we do is look. We're looking for which of them is aromatic. So we know aromatic is 4n plus 2 pi electrons. So all of these guys actually have heteroatoms in them. So we have to think about the heteroatom rule. We know that boron, oopsie, that's ugly, is sp2, and no electrons. So let's go through here. We have 1, 2, 3, 4, 5, 6 pi electrons. So if it's sp2, it'll be aromatic. If it's sp3, it's always going to be Na. So this one is aromatic. This one, right off the bat, we see this sp3 carbon. So this one is non-aromatic. For this one, we see the boron. We're going to treat it as if it was a carbon with a plus charge. So we have 1, 2, 3, 4 pi electrons. This would be anti-aromatic. For number 4, we see this sp3 carbon again. So we know this is non-aromatic. I don't know why the A came out squiggly, but that's fine. And then here we see that sp3 carbon. So this, once again, is non-aromatic. So the only aromatic answer is A. Any questions? Okay. All right, so this is one of the ones where it's like really wordy for no reason. So based on blah, 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 non-aromatic. So remember, in order to be non-aromatic, you're just looking for something that breaks a rule. We already did this guy in the example before. We know that he's cyclic planar, fully conjugated, 4 pi electrons, so it's anti-aromatic. This next one, we see it's cyclic planar, fully conjugated. It has the negative charge, so this lone pair. So we have 2 4 pi electrons. 4 pi electrons equals anti-aromatic. Oop, we found an sp3. So we know this is non-aromatic. So I'm just going to circle. If we move over here, 2, 4, 6 pi electrons, we know this is aromatic. All right, so this next one can be kind of tricky because it's an 8-membered ring, which means it might not be planar. So if it remains planar, it has 2, 4, 6, 8 pi electrons. So it would be anti-aromatic. If it's non-planar, it's going to be non-aromatic. So you guys tell me, which one is more stable, planar or non-planar? Non, exactly. I agree. So this one is going to be non-aromatic, and it will be non-planar. So the second row, we already did this one. We said that sp2 is more, we said that sp2 would be more stable than sp3. Therefore, this is sp2, and this is aromatic. All right, so this is another one of those 8-membered ring situations. So if it's planar, it will have 2, 4, 6, 8, 10 pi electrons. And if it's non-planar, it'll be non-aromatic. So someone please tell me, 10 pi electrons, is that aromatic or is that anti-aromatic? Aromatic, cool. So I think that this guy will stay planar and it will be aromatic. Next up, first and foremost, we see that sp3 carbon, so we know it's non-aromatic. For the last one, we see that this one has a plus charge, so it is cyclic planar fully conjugated, and there are 2, 4, 6 pi electrons, which make this aromatic. So we see that 3, 5, and 8 are all the correct answers. Or they're all non-aromatic, I should say. So we see... So the answer here is supposed to be... I don't know if I cut it off or something, but all 3 of those would be correct. Any questions on this one? Okay, cool. So going to this one. Alrighty. So this is an example where he shows you the minus, but he doesn't give you... Sorry, before we move on, someone said every time we see an 8-membered ring, we do this. Yeah, so whenever you see an 8-membered ring, you want to do planar versus non-planar, just like we do sp2 versus sp3, to figure out where it's more stable. Okay. So, which of the structures would be aromatic? What I was saying is this one, it gives you the minus, but it doesn't show you the electrons. So I like to draw them in. I don't know if you're able to do that on your exam because it's on Canvas, but keep note of them at least. And these spectator ions, excuse me, I don't know why it escaped me for a second. The spectator ions are going to not really do anything. They're just there to show you the charge. So I like to get rid of them because sometimes they trip people up. Okay, so read the question. Which one is aromatic? So you're looking for aromatic. And right off the bat, the first thing I see is sp3 carbon. So this is non-aromatic. All right, so we've seen a couple of these examples before. Let's start with this one. 2, 4, 6, 8 pi electrons. We know this is anti-aromatic. We just did this one, and we said that it's going to be planar, and it's going to be aromatic. So I'm going to write that down here. And we already have our answer, but just so you guys kind of have it in your notes, let's do the rest of these. Cyclic, planar, fully conjugated, 4 pi electrons. So it's anti-aromatic. And this last guy has a carbocation instead of an anion. So we have 1, 2, 3, 4 pi electrons. And it's anti-aromatic. And someone asked a question, so let me zoom out. So someone asked how many electrons would there be here. So let's go ahead and count together. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 pi electrons. I know the counting electrons part can be tricky. So just remember each double bond counts for 2 electrons, and then each lone pair is 2, and a radical is just 1. So the answer here, I realized I didn't highlight it for you, is B, or number 2. I'm sorry if you hear like a weird noise in the background. There's like a fan or something. Okay. Again, we're looking for aromatic. And first thing I see, sp3. So this has to be non-aromatic. And now we have the anion, the cation, the anion, and the radical. And we know that if there's an odd number of radicals, it automatically has to be what? Non-aromatic, exactly. So odd number of radicals means automatic non-aromatic. So let's do the cation. We have 1, 2, 3, 4. And here we have 6 pi electrons. So we know this is anti-aromatic and this is aromatic. So our answer would be C. Any questions on this one? All right. Again, if I scroll past and you have a question on a previous one, don't be afraid to ask. All right, so I did it again. I cut off some of the answer choices. All right, we'll just go through. Now we're looking for anti-aromatic, and as you can see, this one actually has the same exact answer choices as a previous one we did that was asking for non-aromatic, I believe. So it's really helpful if you like remember certain ones. For example, I know off the top of my head that this has to be anti-aromatic. So I'm going to go through and point at them, and you guys tell me, are they A, Na, or AA? So what do we think about number 2? Okay, so we got some non and some anti. So I'm going to say anti-aromatic, and the reason is it is cyclic, planar, and fully conjugated, and it has 4 pi electrons. And for that reason, it's going to be anti. But this next one is non, yes. So the next one is non because it's sp3. Cool. And what about this guy? Oh, that one was a quick one. Yes, I agree. Aromatic. How about this one? So we got a couple different answers so far. Remember, think about the planar rule. Na, yes. So it's an 8-membered ring. If it has 1, 2, 3, 4, 5, 6, 7, 8, it's either anti or non-aromatic, and we go with non-aromatic. What about this guy? I agree. It's going to be aromatic. And what is the hybridization of that nitrogen? sp2. Cool. All right. So, excuse me. This one is planar and aromatic. Cool. This next one, automatically, we know it's non-aromatic because of this sp3. And last but not least, exactly, aromatic. Cool. So we know that 1, 2, 1 and 2 are the anti-choices. Again, I cut off the answer choices, so that's my bad. And then someone asked, could I explain 5? So yes, I can. So basically, we know that this guy can either be planar, it can stay on the plane, it can be flat, and it's going to be a little bit unstable if it does that. But if staying flat allows it to be aromatic, it chooses to undergo that ring strain or deal with the ring strain. If it's non-planar, it has to automatically be non-aromatic. And these kind of rings like to bend out of the plane and be non-aromatic. But as I said, if being planar allows it to be aromatic, it chooses to be planar. In this case, we have 2, 4, 6, 8 pi electrons, and 8 would be anti-aromatic. So in this case, we choose to bend out of the plane and be non-aromatic. Whereas in this example, okay, in this example, planar would give you 10 pi electrons, and 10 pi electrons would give us aromatic. So it would choose to be planar and aromatic. That make a little bit more sense the way I explained it? You're very welcome. Okay, cool. So going on to this one. All right, something we didn't really talk about, but it was in the notes I sent you, is this double bond. So if we have something double bonded to an oxygen outside of the ring, we're just going to pretend this is a carbocation because it's sp3, or excuse me, it's sp2, and it donates 0 electrons. So pretend it's a carbocation. That's what I always do. So we have 1, 2 pi electrons. So this is aromatic. This one is a whole hot mess. It's not conjugated. It's a whole mess. So we're going to say that's non-aromatic. This one, we have 1, 2, 3, 4 pi electrons. And it's anti-aromatic. And this space is killing me. Okay, and so this last one, we have sp3. So this is non-aromatic. And just to double check, we are looking for aromatic. And the only one that's aromatic is A. Any questions? Okay. The carbocation, so basically what I was saying about it is if you have a carbonyl, like a double bond going out of the ring, not like, for example, something like this, right? If it's going out of the ring, you essentially just treat it like a carbocation because it is sp2 and it has no electrons. So again, double bond out of the ring, sp2, no electrons, treat it like a carbocation. Okay. So there's a whole bunch of aromatic questions. I'm just going to skip a couple of them. It's all the same stuff, and we can come back to them at the end if we have time. So this is an aromatic question, but it's like a word problem. So what this is basically saying is there are 2 resonance structures of benzene. And then it's saying which of the following are true. What do you guys think? Just reading this. I'll give you a moment. And I'm going to just draw it out like this. Okay, so a couple people said D, and I'm going to agree. That rhymed. So, basically, the benzene has a completely conjugated ring system, right? And that means the electrons are delocalized around the whole ring, right? And what this means is technically neither of these two are correct because the electrons are constantly moving. So neither of these is an accurate representation. This is more of an accurate representation. And then someone said that they picked D, but why couldn't it be B? So the reason it's not B is because technically it's not going to be in those states. It's not like it's going back and forth between those states. It's more so like the electrons are all around the ring all the time, if that makes sense. Like it's such a rapid movement of electrons that you can't define them in this way. Does that sort of kind of make sense? This semester, or the semester I took this class, this question was so much. Yeah, I hated it so much. My biggest problem with it was A, because it says they're equally correct. I mean, that's technically true. Like, neither of them are correct, but those are equally incorrect. Anyway, it's just me rambling. I don't like this question, but Dr. West tends to like similar questions. Okay, so something that I know Dr. West covered a lot, so I didn't really mention it. I'm going to say it now, is when we have a benzene ring and we have something on it, let's just call it X, right? The spot next to X is ortho. The next one is meta. And the lowest is para. And we call that O, M, P. All right, so the way I remember it is pretty dumb, but I will show you. So if we have something here, X, and let's say we have Y, right? Y in the meta position gives you an M. So M for meta. Ta-da! All right. The next one is para. I think of para as the South Pole. So it's the opposite pole. P for pole. And ortho, I don't know, it just makes sense. Like, they're right next to each other. They're oriented next to each other. I think of it in like a bio type of way. There's like ortho species, which means that they develop like next to each other. Don't worry about it. If you've never taken evolution, you don't know what I'm talking about. Ortho, just remember, is next door. All right. So when we're naming benzene rings, this is important. That's why I bring it up. So between OH and chlorine, which one is going to be the, what's the word? Like the important one that we care about? What is the word that I am thinking of? Yes, you guys are right. It is the OH. So the OH is the priority. So the OH is a priority group. Yes. So we are going to compare everything to the OH. And so we have ortho, ortho, meta, meta, para. And we also know that the base that looks like so is a phenol. Why is it a phenol and not a benzyl alcohol? No, bend, exactly. And someone asked a question. I will answer it in 1 second. So this would be a benzyl alcohol. And we don't want that. All right, so it's a phenol, and we know chlorine is named chloro. So we're going to go ahead and call this orthochlorophenol. All right, so yeah, this is a good point. Someone just repeated what I said. O is for next or. And someone else said, is there any way this will be ready after this session? Yeah, so I will try to put this up like right after, because I know it's like part of the exam review and your exam is tomorrow. So I will try to get it up as soon as possible right after the session. Someone asked if this is material from the last exam, so this is going to be stuff included in this exam. For the naming stuff, he might not include naming in this chapter. The only reason I gave you guys 2 examples of naming is because he did cover it last class. So I just wanted to get that out there. Yeah, his chapter 14 has IUPAC naming things. So, molecular orbitals for benzene. So I'm going to very quickly open this up. And we're going to talk about the molecular orbital theory of aromatic rings. So we already went over MO theory in a lot of detail for chapter 12. For chapter 13. So when we're talking about benzene or any kind of aromatic compound, it's going to be very similar, but there's going to be ever so slight differences. The biggest difference is going to be that for benzene, you're going to draw benzene out like so, right? And we're just going to go ahead and make a line for every point in benzene. Ta-da! And we know that there are 6 pi electrons, and we have to figure out how to put these in. So now, instead of having 1 orbital per energy level, we actually have multiple orbitals per energy level. So when we're filling it up, it goes 1, 2, 3, 4, 4, and then we go back 5, 6. The reason we do this, again, is because we have multiple orbitals on the same energy level. The name for this is called degenerate orbitals. So again, degenerate orbitals are multiple orbitals on the same energy level. And for the number of atomic and molecular orbitals, we basically are going to count the double bonds. And each end of the double bonds has a p orbital. Nah, that's ugly, but that's fine. And we also have a p orbital or an atomic orbital when we have a cation, an anion, or a radical. So each of these guys has an electron in it. Ta-da! And okay, so when we're doing the number of bonding and antibonding orbitals, so one thing you have to keep in mind is the half rule is still going to apply, but now we're looking at the number of energy levels, not the number of orbitals per se. So when we cut it in half, we cut the energy levels in half. We had 1, 2, 3, 4. So 2 of these levels will be bonding, 2 of these levels will be antibonding. So we have pi 1, 2, and 3 are bonding. Pi 4, pi 5, and pi 6 are all going to be antibonding. Everything else is going to be exactly the same. So let's say this becomes excited. The electrons from pi 3 are going to go to pi 4. And I also just wrote everything out for you guys because I know we didn't really get to cover it in SI. We ran out of time. But the biggest thing I want you to remember is the degenerate orbital thing. And okay, so now when we're talking about the cyclic dyne, I'm going to redraw it out. So I don't know why this is. I think someone just drew it and then they turned out to be right. So that's how we do it now. But we're going to tilt it on its side, kind of like benzene. And we're going to, again, draw an orbital at each point. And now we have 4 pi electrons. So we start down here, 1, 2. These 2 orbitals are degenerate, so we go 1, 2, and now we're out of electrons. So while I number these, okay, so this is an anti-aromatic ring. And we can see the reason it's so unstable is because it has 2 half-filled energy levels. Or, excuse me, molecular orbitals. 2 half-filled molecular orbitals. And yes, so this is technically how we do it for cyclic molecules, but not just cyclic aromatic molecules. And wink, wink, nudge, nudge, you only need to know these 2 for Dr. West's exam. The one thing to note, here we're still going to cut in half, right? And so this will be bonding. This will be antibonding. And pi 2 and pi 3 will be non-bonding. This is where people get confused because they're like, wait, Rosemary, but we had 4. Why don't we just do these 2 are bonding and these 2 are antibonding? We have to stick to energy levels. So we have to cut the energy levels in half, and the 2 molecular orbitals on the line are going to be non-bonding. And this is anti-aromatic, you're correct. Well, okay, so what I mean by aromatic molecules is like aromatic and anti-aromatic because, you know what, why don't I just say fully conjugated cyclic molecules? That makes more sense. So this is how you do it for fully conjugated molecules. And yes, the attendance link, if you haven't signed that yet, please do so. So for HOMO and LUMO, it's pretty much the same. So in the benzene one, pi 3 is the highest numbered orbital that has electrons. So that would be the HOMO. And pi 4 will be the LUMO. For here, it's a little bit more confusing, but the HOMO would be pi 3 again. And the LUMO would be pi 4. And again, I just recommend looking at this because this has all the information you'll need for this concept. All right, now back to practice problems. You're very welcome. Okay, so for the molecular orbital of benzene, how many pairs of degenerate high antibonding molecular orbitals are there? I'll bring this back for this question. So I want you guys to tell me, how many degenerate pairs of antibonding orbitals are there? One, I agree, because there are two orbitals that are antibonding, and so they make one pair. So there is one pair of degenerate orbitals. Okay, it would be so cool if this didn't do that. So we're going to say one pair of degenerate orbitals, aka two single degenerate orbitals. Okay, so something you just have to know, xylene equals benzene with two methyls. So it's dimethylbenzene. And toluene is a benzene with one methyl. This is not a methyl. I will put a file of common benzene names to know. I think that he's going to wait until the next exam to give you this, but again, he covered it, so he might give it to you on this exam. Just know these common names. Okay. So, which of the following dienophiles is most active to Diels-Alder? We know right off the bat, we are looking for electron withdrawing groups. This is the only one that has an electron withdrawing group. So, as a couple people said, this will be the answer. All right. So for this guy, it's a Diels-Alder question, and I'm going to show you how to do it real fast. So we have a 5-membered ring with a double bond. So we know we're going to have bicyclic with one carbon in the bridgehead. This is the only answer that is bicyclic with one carbon in the bridgehead. So it's C. Super quick. So again, 5-membered ring. We know that we're going to end up with bicyclic and one carbon in the bridgehead. This is the only one who matches. You don't even have to do a reaction for this one. All right, so for this one, remember what I said about reversible. So reversible means equilibrium, and it means thermodynamic control. And we know that the lowest activation energy is the kinetic product. And we know that the lowest potential energy is the thermo product. And we know this is the most stable. Right? So now it's asking you like what is implied by this diagram, right? And if you know this information, you'll be able to answer any question like this. So the less stable product forms more rapidly. No, because we know kinetic product and thermo are together. It's under thermodynamic control. So the most rapid product will be the most stable one. We know that product B will be predominated. No, that is the less stable one. That's not true. We don't have enough information, but we can say that B is correct because the more stable product forms the most rapidly. Most stable forms more rapidly. Any questions about this one?
Rose,
Yeah.
I didn't have a question about this. It was just kind of like something from the exam review, like a small little thing.
Mm-hmm.
Were you able to find out if the pentadiene had a radical or if it was just like um
I
yeah.
haven't gotten to watch the lecture yet.
Mhm.
I'm gonna do that today. I just have like an exam later, so I was like studying for
Oh,
that.
oh, okay.
But
Yeah.
but I will look today, yeah.
Okay. Thank you. And my last question was I just did a weekly assignment and I just didn't understand what he meant. The question was the pi electrons in benzene is located, and the answer was above and below the plane of the ring. I didn't know what that meant, above and below the plane of the ring.
Yes, okay. So basically what happens is we know that benzene is gonna, could you not, is gonna be planar, right? Because in order to be aromatic, you have to be cyclic, planar, and fully conjugated.
Mhm.
And these are so ugly, but you have these pi electrons, right? Or
Yes.
these p orbitals, and the pi electrons, which I'm going to draw as like blue, are going to be up here swirling around, or they could be on the bottom swirling around.
Okay.
So there's also this whole thing about like a current. So there's going to be like an electrical current happening here. Don't worry about that. You won't be tested on that. Just know that the electrons are flowing above the plane and below the plane because that's where the p orbitals are.
Okay. Thank you.
You're welcome. I don't know why I said never mind. You're very welcome. Okay, cool. So this is one that we did in the exam review, and very quickly we can get the answer because this is a dienophile and a dienophile. Garbage. Um, this is a diene and a dienophile, and it looks pretty good. This is a diene and a dienophile, but this does not match this because you would get a bicyclic compound. Garbage. Again, this makes no sense. Garbage. The only one that makes sense is this one. And then you can do the reaction just to double check, but since we're kind of short on time, I'm just going to go ahead and tell you the answer is D. Ta-da. This next one is very similar. So we have one carbon in the bridgehead. That means we had to start with a 5-membered ring. This one and this one are clearly not it. And the reason I say they're clearly not it is because you're already starting with a bicyclic. You can't start with a bicyclic and get a bicyclic. Now, this one is 2 dienophiles. That can't be it. And you're stuck between these two. We know that between these two, the answer is B because these two groups are pointing the same direction. And so we had to have a cis product. A cis dienophile to get a cis product. Exactly. So 2 is going to be correct. And yes, someone said it, they're kind of tricking you between cis and trans to see if you know your stuff. All right. So a reaction that is under kinetic control is going to give you the kinetic product. And so the only one of these answer choices that is telling you or is explaining the kinetic product is going to be this guy. So again, remember, we're never doing greatest. If you see greatest, garbage. Lowest potential energy, we know is thermo. Most stable, we know is thermo. And we know that this often is a product, like B is often a product of C, but the best answer would be C. So the definition of the kinetic product is the smallest amount of free energy of activation. And so, yes, B is often true, but it's not necessarily true. That one's a tricky one. Okay, so 70, I'm going to give you the answer, but don't worry too much about it. So all you have to know is single bonds get shorter when they're close to double and triple bonds. So if you're looking for the shortest single bond, you're going to find it here because it's a single bond in between two triple bonds. So it's going to be extra short. And so E is the correct answer. I'll say it again. But okay, so the shortest carbon-carbon single bond is going to be the one closest to like a triple bond or a double bond. And here we have one single bond in between two triple bonds. So the single bond gets shorter. Okay, isolated diene. Tell me right quick, what is it? 4, yes, and all the rest of them are conjugated. And yes, just to recap, the last one you are correct. The single bond gets shorter the closer they are to triple bonds. Correct. Alrighty. And then 53 is D. That's the only isolated one. Everything else is conjugated. Okay, so here it's asking which of the following dienes do you expect to be most stable? And he will definitely ask you something like this. What you need to, first of all, what I see first is this one is cumulated. So we know that that's not the right answer. And then we see that these are super far away from each other. These are kind of close. These are far away. These are kind of close. So we also know that it can't be A or C, not a star, we need an X, because those are isolated. Between B and D, both of those are conjugated, but D is going to be more reactive because it has a less stable double bond here. This one has a more substituted double bond, so B will be the correct answer. Any questions on that one? I know I kind of said it weird. So the reason it's B and not D is because both of these double bonds are more substituted than these double bonds. So here we have a monosubstituted double bond. Here they're both disubstituted. Yes, and more substituted equals more stable. You are correct. More substituted equals more stable. Okay, so I have another session that I have to go to for tutoring, so I'm just going to very quickly give you the answers to a couple of these. So this is the most stable carbocation because it is allylic and it's tertiary. This one we've already done. You can just look at the answer from the thingamajiggy. We've already pretty much answered all of those questions, but I did want to show you this one. Okay, so this is a reduction reaction, and we are going to reduce this one we leave this one absolutely unchanged. So this is incorrect because it flipped. This is incorrect because it's flipped. And these two are just enantiomers of one another. You're going to get both enantiomers, so you get a mix of 1 and 3. So when you're doing this, make sure you look at, the other carbon to make sure they weren't changed. If they were changed, it's wrong. Another one that students tend to get wrong is this resonance structure one. We're never going to have the minus here and the plus here. So number 2 is not an important structure. This, however, is an important structure, because if we move the electrons here, we get this guy. Okay. And then I wanted to do one retro Grignard because we hadn't done any of those in the review. So these are pretty straightforward. What we're going to do is take this guy, right? And we know we needed a carbonyl and an alkyl halide. And we know that wherever the oxygen is attached is where the carbonyl was. So we're going to go ahead and break this bond. And we get O. And we get X. Like that. And these are not like one thing. Those are two separate things. And the only answer that matches is this one. Do a couple of these types of examples just so you can see what I mean. But again, the side with the OH becomes the ketone. And the side that's kind of just attached there is the carbonyl, the carbon chain that comes from the Grignard. And the last one I really want to show you is this one. So we see there's 1 oxygen, 2 oxygen, 1 oxygen, 2 oxygen. And we see that this was reduced from a ketone to an alcohol. And this was reduced from an ester to an alcohol. So, it was B, not D, for the one above. And the reason was because this was a 6-membered ring and this was a 5-membered ring. All right, back to this one. So since we were able to do the ketone and the ester, we know ketone is group 1, ester is group 2. The only one that's able to reduce both groups is LiAlH4. And then I can scroll up to the one above, unless anyone has any questions on this one. He'll definitely ask you a reducing question like this, which it like has multiple oxygen groups, and you have to figure out like if it was a strong or a weak reagent. So pay attention to that. I don't know which one you're talking about, so I'm just gonna do this so you can see all of these ones. And yes, so I have to go. But if you have any questions, please feel free to email me. I'm sending the attendance link one more time, and I will stop the recording.